It's great to be here. Thanks, Alan, for that very kind introduction. Although I would disagree with you. If you were going to get a Google guy to celebrate the birth of the internet, you should have got Vint Cerf. But he can't be here today, so we'll have to make do with me. Thank you all for coming. Thank you for you guys standing in the back in solidarity with you. I'll stand up throughout the whole lecture. And I want to talk today, the title of the talk is The Unreasonable Effectiveness of Data. And for that I mean for understanding the world and for doing things with the knowledge. So let's look at what it means to understand the world. And here's the traditional approach. That you get a guy, his name's Isaac, and he observes something about the world, and then he gets an idea, and then the hard part, he formulates that idea into a theory, and then you go and test and refine the theory and so on. And when you get it working, then you can do something useful, like the kind of stuff we did at NASA, of put ships into the right orbit and so on. Now, this talk gets its title from Eugene Wigner, who wrote an article called The Unreasonable Effectiveness of Mathematics, in which he said it was a miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics. He said it's a wonderful gift which we neither understand nor deserve. So what he meant is, isn't it amazing that we can do so much with these short mathematical equations, the F equals ma, the E equals mc squared, the PV equals nRT, and so on and so on. How is mathematics so succinct and so powerful in describing the world? And he speculates on the philosophical reasons for that. But I think only a physicist would speculate on that. If he was a biologist, he wouldn't be going on and on about how short the equations were. And if he were a sociologist, even more so. And so there are small parts about the world that can be described with very short equations, but we won't be talking about them here. Instead, we'll be talking about the messier parts and trying to figure out what we can do with those messy parts if we can't come up with a short equation. Now, the next figure in the story is a statistician, George Box, who wrote, essentially, all models are wrong, but some are useful. And so what he said is even the beautiful models like F equals ma are not quite right, and Einstein and others come along and refine them a little bit. And if you're going to be wrong anyways, then why not just be pragmatic about it and say, let's find something we can use and get the results that we need and not worry about being absolutely right. So it's kind of a different approach to solving the problem. So let's take Box's inspiration and try to solve a problem with a simple model. And we'll take as the problem predicting the dates of the next lunar eclipse. Now, I could take Newton's approach and work out everything with F equals ma and the gravitational constants and so on, but then I'd have to remember all that physics stuff. So what's a simpler model? Well, I took my favorite simple model. So I typed in lunar eclipse dates, and I clicked on the #1 result because I trust the result ordering. And I got this page. And it was really good. And it told me all the answers for all the dates I needed. The page is a little bit old, so if I want to go into next year, I'll need another page. But this was a really good result. Now, in some sense, this is cheating, because somebody who did know about F equals ma had to generate these results. But in another sense, it's not cheating, because this is just as much a part of the world as those equations and the moon itself are. This is a part of the world and happened to be generated by another person. But we're observing this part of the world and getting the answer. So we really see this progression from, I've picked out these three people to emphasize the 3 points of view. So Newton, with this scientific approach, saying it's all up to the scientists to observe the world and come up with a theory. Then this is Ed Feigenbaum, representing the good old-fashioned AI, or expert system approach, saying, yes, the human has to do that, but once we have those humans, and we have some experts out there in the world, maybe we can automate what they do by going and interviewing the experts, figuring out what they know, encoding what they know in a computer program, and then we can run that program and duplicate their efforts. But it's still, all the effort has to be done by the human first. Then the final approach, characterized here by Udaya Pearl, is the statistical machine learning approach, where we say we don't need to have an expert tell us a theory. Maybe we can gather enough data and run statistics over that, and that will tell us the answer without having to have an expert. And So we'll see how well that approach works. And we'll look at two different domains. First, images, and then text. So let's start with images. And in fact, let's start all the way back. So here's some images in a cave in Lascaux. And when Pablo Picasso was showing this, he said, we've learned nothing in 12,000 years. Here's one of Picasso's drawings, not so much different. It turns out he wasn't quite right, because later on they did more accurate radioisotope dating, and it was more like 18,000 years, not 12,000. So Picasso's able to come up with this. And then there's a period of technological innovation between 18,000 years ago and today. And in the 1840s or so, Brady and others were using a new technology to generate pictures like this. Now, they don't look all that much different, but the technology to produce them was quite different. And the level of accuracy and so on, the quickness of producing them revolutionized the game a little bit. But the results are the same. And now we have to have another revolution that came in the coming years of this. And let's see if it actually works. Yes. So if we string together 24 of these photos per second, now we get a qualitatively different approach. So now what has been the same for 18,000 years now becomes a brand new experience just because we have more images stacked up together. And I want to look at examples of, say, other cases where we can have more give us a qualitatively different experience rather than just a quantitative. Okay, so we're going to look at a set of problems and see how we can approach them by having more of this data. First problem we want to look at is scene completion. And this is work by Hayes and Efros at CMU. Most of the work I show you today is done at Google, but this was done at CMU. And they take as their task fixing up this picture. So say you're on vacation, you take this picture, you like the sweep of the coast in the background, but the rooftops in the foreground are kind of annoying and you'd like to get rid of them. Now, if you're a little bit handy in Photoshop, you can probably go in and outline that, but you really got to be a Photoshop expert to fill in that blank spot. And that's the task they took upon themselves. Now, the approach they took to that task was to say, let's build a library of images and figure out which one we can paste into that empty hole. So they've got this library. They wrote an algorithm to go through it and paste it in, and this is the result. So this is pretty impressive. Now, for me, as a medium good Photoshop user, I'd be very happy if I could just match the color of the ocean and put that in. But they've gone well beyond that, and they figured out that there should be boats there and not, say, cars or something else in the middle of the ocean. Now, how do they do that? Well, they did that by matching against the images, of course. And if you think about it, they've really changed the way we think about the whole process of computer science. Now, when I was in school, they showed us pictures like that, and they said, you know, there's this whole system here, but really what matters is the thing that's in the middle of the diagram. It's always the thing in the middle that's the important part. And so computer science is the study of programs and programming languages and programming algorithms and so on. And yeah, there's some input and output, and there's some data, and the people in the other building in the EE department will tell you about hardware, but really let's focus on the program. And of course, Efros and Hayes did a great job of programming, very innovative algorithm. But really what made this work was the data. That if they didn't have that picture of the sea with the boats in it, they wouldn't have been able to come up with a good result. And we see in this example this idea of a data threshold. When they started off, they found a library of 1,000 or so images, and they tried it out, and most of the time it failed and didn't give them anything good, but there were a few tantalizingly good results like the one I showed. Now, what could you do at that point? Well, one, you could give up, say it's failing most of the time, I guess it was a bad idea. Two, you could work really hard on the algorithm, say, can I come up with a better algorithm? Or three, you could go out and say, let's build a better library of pictures, and that's what they did. So rather than stopping at 1,000 images, they went out and got millions of images, and their performance, the percent of good quality solutions, passed this threshold and went from really bad to really good. And this is the kind of result we see on many problems. Okay, I just wanted to bring it back to Google a little and show another example. I won't talk too much about it. This is the task of scene carving, which is figuring out what the good and bad parts of a scene are to reformat it. And so here we're taking widescreen YouTube videos and reformatting them for a small screen. And you don't want to just squish them, or else all the people would look really skinny. Rather, you want to cut out the bad bits and leave the good bits. And this work by Grundmann and Quattro did that. It figured out what's the important stuff that you want to leave on scene, and what's the bad stuff that you can cut out to make it fit in the right format. Okay, now let's move on from these image models and talk about text models. And first I wanted to pause for just a second and commemorate Fred Jelinek, who passed away last week and was really one of the founders of this field of statistical natural language processing, mostly working in speech recognition. But his ideas really permeated everything that we do in the modern world having to do with text. And so he was a real leader. He stayed in academia when all his colleagues were applying their modeling techniques to financial models and making lots of money. And he helped push the field forward, so we all owe him a great debt. All right, so we want to deal with text data. To start that out, we want to gather some data that's useful. Like Hayes and Ethros gathered these millions of images, we want to have something to go on. And we could have the raw text, but it's turned out that the field has agreed that summarizing that text is more useful. And Google has helped that by publishing a corpus of n-grams. N-gram is a sequence of n consecutive words. So we went out on the web and found 1 trillion words. And we tried to eliminate all the bad spammy stuff and all the duplicates. And we didn't do a completely good job of eliminating that, but we cleaned it up quite a bit. So that's 95 billion sentences, 13 million unique words, and then those various numbers of 2, 3, 4, and 5 word sequences. So we would tell you each of those sequences and how many times they occurred. For example, here's an excerpt from the middle of the 4-gram sequences telling you how often each of these 4-word sequences occurred. And you start to get a feeling, and this is just a very small excerpt, of course. And so there's lots and lots of information for what you can survey, much more than you would see in a dictionary or encyclopedia. So there's a lot of information there, but of course it's uninterpreted information. In order to make sense of it, all we have is the raw data. Programs that want to make sense of it have to do that on their own. So what can you do with this type of data? And just in terms of counting number of words. Well, let's go back to our original task of doing orbital mechanics. And I'm going to show you how to do orbital mechanics with no telescope, with no F equals ma, just using text. And we're going to do that. We're going to answer 2 questions. One, what is the period of the orbit of the moon around the Earth? And the other, what is the period of the orbit of the Earth around the sun? And how did I do that? Well, I went to my favorite tool. And this time, I went to Google Trends and put in these 2 queries, full moon and ice cream. And you see, this is the histogram of the popularity of the queries over time. And if you look at those peaks for full moon in blue, and you measure the distance between the peaks, it works out to 28 days. And then in the red, we have ice cream. You can see popular in the summer, not so much in the winter, and measure the distance between the peaks there, and it works out to 365 days. So we've succeeded. The world as a whole, our set of users have answered these physics questions for us, and we did it just by counting words. All right, so that's kind of fun, but on a more serious note, there's other things that you can use counting words for. And of course, we built Google Trends so that our advertising customers could help build their business and see what people are searching for and therefore what they should be advertising for and so on. But on top of that infrastructure, we also built these flu trends. And here you can go into a particular locality, a country or city, and see how often people are searching for things that indicate that they may be getting the flu. And here we track it over time. We show this year's curve in dark blue and past years in light blue, and we can see this year is fine. It's following the normal kinds of trends. But last year at this time was that very high curve that peaks in October, and it was starting to look kind of bad. It was 3 or 4 months earlier than the peak usually occurs and higher than most years. If that had kept going up, it would have been a really bad epidemic. And so it was important to be able to track that and understand what was happening. And unfortunately, in late October, it started to come back down, and we were okay. Now, we track these and we put these statistics up, and we can do it kind of instantaneously. As soon as people are searching, we get the results up the same day. Now, we calibrate this against the reports that we get back from the Centers for Disease Control, and the way they get their numbers is by aggregating statistics that come from doctors, from emergency rooms, from pharmacies and drugstores that are dispensing drugs and so on. But it takes them about 3 weeks to gather all this data for it to all trickle in. So what we're doing essentially is predicting the present. It's really hard to predict the future. It's easier to predict the present. And this is actually useful in some cases, because all the CDC can predict is 3 weeks in the past. If we can predict the present, we're 3 weeks ahead of them. And if there was a big epidemic, that could be a crucial 3 weeks. All right, so that's one task there. But so far, we've done just strict counting. Maybe we can do something that's a little cleverer than that, where we need some more algorithmic work. So another task that a lot of people in natural language processing have tackled is word-sensitive disambiguation. And here the task is we give you some training data, and you train up a model that discriminates between two senses of a word. So we're going to give you a test sentence. It's going to have the word bank in it, and you tell us, is that bank 1, the river bank, or bank 2, the money bank? And after being given a set of sentences that have those words in it, then you get the test. And Banco and Brill of Microsoft Research did a meta-survey of papers in this genre and talked about the results. And what they point out is that the academic game is played along this axis. So in the academic game, you take a standard test set here of 1 million words of training data, and you develop your algorithm, and you run it on the training data, and you report your score on the test cases. And if your algorithm is this one in X up there that scores 85%, then you get to publish a paper, because you're better than anybody else who had published a paper before. But what Banco and Brill pointed out is there's a lot more room along this dimension than there is along that dimension. And in fact, if instead of trying to be clever about a new algorithm, if you just went out and gathered 10 million words of training data, now all of a sudden the very worst published algorithm is performing better than the very best algorithm did at 1 million words. And similarly, if you go out to 100 million words, we get the same phenomenon. Now, eventually, the additional information that you get from more data starts to diminish. And when we get out to 1 billion words, now that's no longer the case. It's more mixed results. But if you're going to do an analysis of what algorithm is best, let's start that analysis out there at 1 billion words. Let's not start it out here where the answers are different. So that's the lesson there, and you can see the difference in results as well. We get up to about 95% rather than 85% by having this additional data. Okay, so that shows that more data works well for word sense disambiguation. Let's move on to another task. This is the task of word segmentation, one that may be not that familiar to English speakers, but in Chinese and several other languages, there are no spaces between words. And in order to read this, you have to know, is the first word consisting of 1 character or 2 characters or what? Now, for those of you like me who don't speak Chinese, let's flip it back to English. Let's pretend English didn't have any spaces in it and see, can you read that? And the answer is, yeah, it's not that hard. It's easier when there's spaces there, but it's not that hard to read. Now, the important question, of course, is what did you need to do, or what did you need to know in order to be able to read that? If you had to know everything about English syntax and the semantics of all those words and all their associations, that's going to be really hard to encode into a computer. If you had to know less, then maybe we have a hope. So what I'm going to do in the spirit of George Box is blindly go ahead and come up with the simplest model I can. It's probably going to be wrong, but let's see if it's useful. So I'm going to define this function segment of t, which takes the text t and figures out the best segmentation for it. And we'll define that as the maximum over all ways of breaking up the text into a first word and the rest of the words, such that the probability of that sequence of words formed by the first and the best segmentation of the rest is the maximum. So it's sort of just definitional here. And now I'm going to make the model wrong. I'm going to say that the probability of a sequence of words is equal to the product of the probability of each individual word. So I'm saying each word is independent of the others. Now, I know that's wrong. If one word occurs in a sentence, that really affects the neighboring words quite a bit, and then it can affect the words far downstream to some extent. But I'm making this simplifying assumption, and we'll see how well the model goes. And one reason I make that is because I've got that data, that probability of an individual word, that I've got in my n-gram corpus. That's just the counts for the 1 grams, and so those are easy to look up. Now, to segment this text, I go through and I say, what are all the possible first words? It could be just N, N-O, N-O-W, and so on. And then I figure out the probability of the first word that I just get by looking it up. No and now are really common English words. They're about 0.25% each, so those are really high. Other ones, not so much. And then once I've chopped off that first word, then I recursively try to find the probability of the rest of them. And, of course, that's going to vary based on what first word I chose, because are we starting with a good place to start a word or not? And it turns out that the segmentation that starts with now, and in fact, it turns out to be the one that has just the right segmentation that you would expect, has this probability, which is 10 to the 5th times better than any of the other probabilities. So in this case, even with all these wrong assumptions I made, this model does well. And it has the advantage that it all fits on one page. So this is the whole thing. You know, maybe you can read this code, and maybe you can't. You have various backgrounds, but that's not important. I think the important thing is just to note how close a correspondence we have between the mathematical model and the code that implements it. So it's a few lines of probabilistic statements in the mathematical model, and the code's not really that much longer than that. All right. So I said it got the right answer on one example. Of course, we wouldn't want to judge it on one example, so I built a whole test set and ran it, and I came out with 98% word accuracy. That seems pretty good, considering all the assumptions I made. And I'll show you some examples that it gets wrong, so you get a feeling for how well it performs. So here's one to see if you can do better. Go ahead and segment that in your head. My program got base rate sought to, and it should have got base rate sought to. Now, both of those sound pretty good, but it's a test, and one of them has to be right and one of them has to be wrong. Next, try to segment that. My program got small and insignificant, but it should have been small and insignificant. And now what happened here is that in English, the words in and significant are fairly common, especially in, but the word insignificant is much rarer. And so with this independent model of word probability, it chose the first one. And this is an example where that simplifying assumption was probably wrong, because small goes pretty well with insignificant and not so well with significant. So if we had an n-gram model that was looking at 3 or 4 word sequences rather than 1 word sequences, we could have got this one right. We needed a slightly more complex model. Okay, one more example. Try that one. It's a little harder. So my program got G in or mouse go, which I thought was clever, but was completely wrong. And it should have got ginormous ego. And the problem here was this was out of my training data. So for this example, I wanted it to run on the laptop, so I didn't use the full trillion-word corpus. I cut it down to a few billion words. And in the billions of words I had seen, I'd never seen the word ginormous before. And this is always a problem. When you have a probabilistic model and you're estimating the probability of something you've never seen, you don't want to say that's 0, because novel things happen all the time. We don't want to say everything that's novel is impossible. But so you have to have some default assumption of what the probability of something novel is. And it's hard to encode that kind of default well. And in making a simple program, I didn't get that. Okay, so but 98% is pretty good. And is this useful for anything? Well, obviously it's useful for Chinese. For English, maybe not so much. It is useful in verifying input. Often people, when they're typing fast, they make mistakes. They put in an extra space. They leave one out. If you wanted to correct that for them, you might want to have a model like this. And then another place where this is useful is in the sublanguage of URLs, which have the property that they don't have spaces in them and often are multi-word domains that are all squished together. And in fact, some webmasters have made mistakes. where they chose a domain name that has a segmentation into words, which is good, and but there's a second segmentation that they hadn't done. And so put yourself in the shoes of the webmaster who's trying to come up with a domain name for a site that says what Hollywood agent represents what Hollywood stars. They came up with whorepresents.com. And in fact, according to my program, who represents is the most probable segmentation. But there is a number 2 segmentation that they should have thought of. Here's another one. Suppose you have a site that tells you how to find a therapist. You could have... therapistfinder.com. Maybe they should have thought twice. Here's one site that maybe you've seen, tells you how to hire an expert. It's called Experts Exchange. And this one, over time, I guess they realized that something was going on, and now they've registered the domain name that has a hyphen after the S. One more site, all the ones above were pretty literal in choosing the words. The makers of these, they're trying to sell some fine writing instruments. They tried to be a little bit more poetic, and they came up with Penn Island. And I should say, for the first 3, the intended representation was, in fact, the most probable one. For this one, it was not the most probable. There are perhaps some words that occur frequently on the internet that they hadn't accounted for. Okay, so much for segmentation. Let's keep working up the chain to harder and harder problems. And next, I want to do spelling correction. And I was reminded by my colleague, Mehran Sahami, who works on machine learning, and always gets a little upset when he sees the little red squirrely lines underneath his name. I get them under my name, too. And then even more so when he hits the OK button and he's told his name should be Tehran Salami. I don't think he's thinking of changing his name to that. But if you think about it, if you were constrained to writing a spelling corrector that had to match to the dictionary, that's probably about the best you can do. I can't think of any other words that are in a dictionary that would be a better match. And so that's why Google and other online services can't be constrained to a dictionary, because there's too many words like people names, town names, product names. So now iPad is a big hot query. A year ago, that was just a misspelling for iPod. And we can't wait for Merriam-Webster or somebody to say a word is official. We've got to act on it right now. So we have to build a corpus-based approach, where we go out and we find the words on the internet, and we build our spelling model based on that. And under the corpus-based approach, if you tell us Mehran Sahami, we say, yes, that's spelled correctly. If you spell it wrong, we can correct it, because he's not famous enough to be in a dictionary, but by golly, he's on the web, and we've seen that sequence of words before, and we know it's correct. Okay, so how do we build a model? Well, again, we build this probabilistic model, and the first step is just definitional. We want to write a function, correct of W, which takes a word and gives the most probable correction. And just by definition, that's the maximum overall possible correction C that maximizes the probability of C given W. Then we apply Bayes' rule, and it looks like we're going backwards, because now we've got 2 probabilities we have to answer for rather than 1. But these 2 probabilities are easier to compute. The probability of the correction C that we get from estimating from word counts, just like we did before. The probability that C was a correction for W, or W was a corruption of C, that's a little bit harder, because it's harder to get a corpus of spelling errors. We can say this is a spelling error for that than it is to get a corpus of words. There are several places on the web where you can get small ones, and that's what I did for this toy program I run on my laptop. If you're running a service like Google, you start off with something, and then as you run the service, you update it every day. You get a better and better model of what spelling errors people make. All right, so let's look at an example that corresponds to that model. we're going to have the task of correcting THEW. And here's the word THEW. Here's the possible corrections. C, we start generating a list. Now I've denoted the possible edits in terms of what words, what letters are substituted for what other letters, and I put one letter of context around it. And then the P of C, the probability of each word that I get from looking up the counts. And you see up at the top, the is very, very common, most common English word, about 2% of all words. And the other ones are pretty uncommon. The probability of the edits, that you get from your table of edits. And you see that substituting an E for an A is pretty common. That's one of the most common spelling errors because those two vowels sound alike in English. That's about 0.001 of all errors. And of course, the correction of making no correction at all, that's very common. And we put that down as 95%. And in the end, you multiply those two out, and I've scaled there by 1 billion, so there aren't too many zeros going off the end of the page. And it works out that THE is the most probable correction, and sort of feels to me like that's the right answer. You know, the W key is right next to the E, so it's easy to imagine your pinky falling off the E and hitting the W. It's a little bit troublesome to me that THEW comes in so well. It's not too much behind. You know, usually you want to look for factors of 100 or so rather than a factor of 50%. It turns out that THEW is a real word, and it's obsolete. Shakespeare used it. It has something to do with muscles. But you wouldn't really expect it to be so high. And I think the reason it's so high is I think its number of counts is artificially inflated because most of them are probably spelling errors. So my corpus was taken off the web, and most of the counts for THEW probably came not from Shakespeare, but from somebody who was trying to type THE. And I didn't try to clean up the data. It would be better if you could do that. And in fact, that's something that's possible to do. So you can use this idea of expectation maximization, where you take the original data, and then you try to spell correct the data itself using the first model. Then you get a new model, and you iterate that process, and then you can clean it up and take away the bad spelling. But we won't show how to do that. Instead, I'll show you just the very simple model. And again, it still fits on one page. I had to use slightly smaller font, you may notice, so cheating to some extent. And the accuracy has gone down a little. It's only 74% rather than 98%. So spelling is a harder task than segmentation. But it's not too bad. And again, you see down at the bottom, we're just maximizing overall candidates over the probabilities. So the program itself is not that much more complex than the mathematical formulation. And most of the complexity in the program is the search through the candidates. How do we find which letters are one or two, which candidate words are one or two letters away from the word you're given to correct. So that's the approach based on corpus, based on data. And we can compare that to a more traditional rule-based approach. Now, this is taken from HTDig, which is a really nice open source search engine. If you haven't seen it, you should take a look, because it's a great resource. And they have several files having to do with spelling correction, and this is just one of them. And here's the middle of one of those files in which they're trying a good idea, which is to regularize the pronunciation. So they're going through each letter, saying what the pronunciation of that letter is, and then if two words get the same pronunciation, then one might be a spelling error for the other. And so if we can look at it, let's look in the middle there, under case C, it says, now I'm going to try to figure out what the letter C sounds like. And it says, sometimes it sounds like an X if it's in this context, sometimes it sounds like a CH, and so on and so on. Now imagine yourself as the maintainer for this program. So you're given this program, it's a couple thousand lines, you don't understand it, and you have to go through and start making sense of it. So if you were here, you'd say, well, the first thing you want to do is say, is this comment correct? Does that accurately represent the sound rules of English? And I'm not so sure just looking at it. So something's going on when you have a C followed by an IE or a Y. But what about A and O? Those are vowels too. Were they left out by accident, or are they actually a different case than those other vowels? Well, I'd have to play with lots of examples of words before I knew if that was right. Then the second thing I'd have to get right is once I convince myself the comment was right, I'd have to say that this low-level C code actually implements that comment correctly, and do I have an off by one error someplace? So that would take me a while to figure out. And I'd have to go through and do that overall, 2,000 lines or so. But maybe that's not too bad. I think the biggest weakness of an approach like this is, say you're maintaining this and it's going along great, and your boss comes to you and says, congratulations, spelling correction's working great. In fact, it's so good, we want to launch it in all the European languages by next week. So just, do that ever programming thing that you programmer guys do and just fix it up. Right? Well, if I want to make this work in Latvian, first I have to figure out the pronunciation rules for Latvian, and I don't know that. And they're going to be quite different than the English ones. So I'm really going to have to throw out a lot of this code and re-implement it from scratch. Now compare that to this approach, the data-driven approach, where if you tell me I want to launch in all the European languages, I say, okay, give me 1 billion words in each language, or maybe I'll go out and I'll find them on my own. And then I'll build a model for each, and I can't guarantee you they're all going to work as well as English. I'd be worried about Finnish, for example, because I know they got really long words, and it may be hard to correct a really long word rather than correct the shorter English words. But at least I'd have a starting point where I can go from 0 to a reasonable model just by collecting data and running it, rather than having to re-implement everything from scratch. So in some sense, this data-driven approach is the ultimate in agile programming. It allows you to move quickly. All right. Let's go with one more example, even more complex, of machine translation. And we put a big effort into this at Google. We went from 2004, when the sort of state of the art is there was only a few dozen languages in the whole field of machine translation among all the people that were doing it, to now where we're adding dozens of languages per year. Slowed down actually a little bit in 2010, only 6 of them so far, because we're getting to the point where there aren't that many more languages that have enough text available that we can build our models. Here's an example of how well it works. Italian original on the left, our translation on the right. And I've underlined places where there are disfluencies. And you can see it doesn't take more than a sentence or two before you can say, hey, wait a minute, this was not written by a native speaker of this language. Mostly the prepositions are the hardest part to get right, and so it says in when it should have said to, or something like that. But in terms of getting the gist of it and who did what, does pretty well most of the time. Now, we're doing the same process again. Bayes' rule shows up once more. So here we're defining the best English translation of a foreign phrase, F, as the maximum overall translation. Do the Bayes' rule thing. And then we have our answer. So there's 2 models. There's an English model. So if we want to translate from the foreign into English, we want to make sure it's a good sentence of English. So we have what's the probability that the candidate we have is a good sentence of English times the probability that it's a good translation. So this is all nice and theoretical and pure, but as well as being mathematically inclined, we're also realists, and so we experimented some, and we found out that when you raise that first factor to the 1.5 power, you get better results. Now, should we dig up Bayes and notify him that he was wrong? No, I don't think that's it. So I think what's going on here is that we have more confidence in the first model, right? So notice, how do we build this English model? By collecting trillions of words of English, and that's easy to do. So we have a really accurate model of 1, 2, 3, 4, 5, 6, 7 word sequences of English. Now, the second model, the probability of the foreign given the English, how do we get that? Well, we go out and we gather parallel text. So we have to go and find a place where there's one text in one language and corresponding text in the other language. Here I show you an example where I gathered some parallel text in my hotel room in Berlin. It didn't add that much to the total corpus we have. But the brochure had sentence on the left and a sentence on the right that was guaranteed to be translations of each other. And now, if you came to me and said, translate this sentence exactly, I can say, yeah, I can do that. It's this English sentence. I know because I've seen that before. And it reminds me of this story by Borges called The Library of Babel, in which he envisioned a library that had every possible book in it. And in order to make the library finite rather than infinite, he said, we'll limit that to 400-page books. And so there is a finite number of them. There's, the book that has the letter A in every character, and then another book that has the letter A in every character, and then a B in the last character, and so on and so on. Borges may not have really quite understood the implications of exponential numbers, so it'd be hard to fit all those books in a library, but there is a finite number of them. And so if you had such a thing and you were given any book to translate, you could just go, and if you could find the right place on the shelf, you could pull out that translation. Now, of course, we don't have an infinite number of books. We don't even have a 400 pages to the 26 or whatever. We have this finite collection, and we're not always going to get a sentence we've seen before. So we need to break up the input so that we can translate a phrase or an individual word that we've seen before, and then figure out some way to paste them together. So we have this original data, and we know that the whole sentence corresponds to the other whole sentence, but which individual pieces correspond to which pieces? Well, given as it is, we don't know. Maybe Kunst corresponds to art, or maybe it corresponds to culture, or maybe it corresponds to Berlin. This one example doesn't tell us. Or maybe it corresponds to some multi-word phrase. So given this one example, we'd have a very wide probability distribution saying it could be any of those possibilities. But we keep on collecting examples, and we see more and more examples, and we start noticing this pattern that a lot of times when you have Kunst in the German, you have art in the English, and then we build this model that says that's the most probable translation. And then from this one sentence, we can cross those two off. They're taken account of, and now we look at the remaining ones and start to align those. And pretty soon we get to the point where we can do this alignment. And now we've got one-to-one correspondences of phrases and words rather than just of whole sentences. Now we have our bilingual model of translation from German to English. Once we built that model, and that's the hard part, is taking the data and building the model, then we can apply it and decode a candidate sentence online as we get it. And I'll just switch to Chinese now rather than German and say, how do we decode this? Well, we take the first character, and we look it up in our table of probabilities. I don't show the numbers of the probability, but they're sorted in order. So most of the time that we've seen this character before, it said he. Then we go on to the next one, and most of the time we've seen this character, it meant letter. And in terms, if we were just looking at the translation model, now the best translation for those two together would be he letter. But don't forget, we also need the English model. And he letter is not so good in English. But going down that list, his letter is good in English. And we would hope that the probabilities would work out right, so that would sort to the top. But we don't have to only hope. We can also work harder and say we don't have to fetch from our tables one word at a time. We can also fetch phrases and see if we've seen these phrases before. And in fact, we have seen that two-word phrase. And it does mean his letter sometimes, but more frequently than that, it's a proper name. And we can keep going. And in fact, we've seen this three-word phrase, and that confirms the proper name usage. And then we just keep on going through the phrase, picking out bits at a time that are high probability and pasting them together. And then we get the most probable path through, and then that's the answer. Okay, so that's the task of translation. Now, it's all driven off of these probabilistic models. And in fact, we've been able to build models for languages that nobody on the team speaks. And we just turn the crank, and we get the answers out. It is really useful to have somebody who speaks the language, especially at the beginning, because there are problems in what defines a word, and segmentation of the word, and endings, and so on. So it really helps to have some expertise there. But what we don't need is to go all the way through and define all the syntax and semantics of each language. And getting back to Fred Jelinek, who I eulogized earlier, he's famous for saying, and he may or may not have said it, that every time I fire a linguist from my group, my scores go up. Right? Right, so he was the first to say we don't need manual effort to write these grammars, but what we need is good statistics. I don't think he really meant that, and he was a nice guy, and I don't think he really fired people, but it makes for a pithy saying. Okay, now this gives us a translation, and we saw from that first example in Italian that they're not always fluent. And one question is, how does this compare to a real English, real professional translator? And one answer is people have tried giving machine translations and professional translations and then having a multiple choice quiz. So they give you a news article and then they ask you, what happened, A, B, C, or D. And it turns out performance is the same. That the machine translation is just as good as getting the facts across. Another answer is, does it give the right sort of aesthetic feel? And there, it seems like we're doing much worse. And in some sense, the whole task of translation is impossible from an aesthetic point of view. And so here's an illustration. So here's a bit of a poem in Italian about the sun and the moon. And in Italian, the moon is feminine and the sun is masculine. And so there's two meanings of the poem come out. One is there's kind of literal meaning about these objects in the sky, and then there's a metaphorical meaning of a man and a woman. And that's important that both meanings are there in the poem, and it's very explicit in the Italian. Now, if you went to translate this into English, if you just did a word-for-word translation, translate sol into sun and luna into moon, and translate the pronouns into it, then you've lost half of that representation. It's no longer explicitly referring to a man and a woman. Maybe the other words in the poem would bring that out, but not to the degree to which you do it in Italian. So what's the translator to do? Well, one thing you can do is vary the translation of the pronouns. So normally we would say it for the moon, but you could say she for the moon. Why not? You're a poet. You can go ahead and do that. And so you bring that back in and try delicately to balance the number of times you do that so you get the right amount of impression of the male-female part versus the literal part. So in English, it's not so bad. What do you do in a language where the genders are reversed? And some of the Germanic languages are like that. And now, all of a sudden, the whole meaning of the poem is reversed. You swap the sun and the moon. Well, you can't do that because it talks about one of them being bright and so on. So you're kind of stuck. Or what if you go into a language where the two genders are the same? Change the whole meaning of the poem again. So we can't get this exactly right without being completely creative. And I don't have a model for complete creativity. But I did want to show that you can do some of this just with these basic models. And so Dmitry Gensel tried this. And what he did is, well, here's an example. He took a poem from Oscar Wilde, which you see on the left. He took a professionally done translation into French, which is not shown here. And then he translated the French back into English. And he got this on the right. But this wasn't the number one result he got. Instead, what he got is a whole list of probabilities. And you saw how I went through and had all the probabilities for each subsequence. So he generated that list, and he looked at the number one most probable translation for the first line, and then he checked the meter and said, is this the right meter for this poem? And if it wasn't, he threw that translation away, and he went down to the second most probable and said, is that the right meter? He kept on going and going until he found one that fit, and then moved on to the next line, and so on. So there's no aesthetics involved. It's just getting the meter right and accepting a hit in probability, and you get something, and well, it looks like a poem to me. I still say that Oscar's poem is better, but at least this has the right format. So that's saying that this is possible to do. And here's just a graph of proving this point again, that more data still helps, that as we give you more possible translation data, the scores keep going up, and we haven't hit that asymptote yet. And I think there's still plenty of room for us to do more with this and with many other tasks by applying more data. And why don't I throw it open for questions now?
Thanks. So the floor is open for questions.
Yeah.
Back in one of the slides, you talked about the statistical number of answers do you need to get the right optimal search results? So it's for thousands, millions, and billions. Have you found what is the actual number that is that optimal?
Well, it depends on the domain, right? So it's a very schematic chart, and for that task of scene completion, there was the point of improvement was somewhere between the thousands and the millions. But for other tasks, it might be someplace else. I don't think there's a general rule of that's at one point. I think you have to look at each individual task.
Lots of interesting stuff today, but there's been a lot of news about software patents lately. How do you feel about software patents? These algorithms.
Well, you know, I'm not a lawyer. I'm an engineer, and I'd be happier if the whole thing went away and we didn't have to deal with them. But we do. So, you know, I leave that to those guys, and we try to do what we do, and you know, not infringe on patents, and wish that everybody could just build the best systems without having to worry about it. Yeah.
Well, all the models you showed us were unsupervised, but not all tasks you see have been used.
Right.
There's always a way you can come up with an unsupervised way to solve a given problem, or are there some tasks that are only tractable using supervised?
Yeah.
Could you repeat the question just for the
Right. So the question was about supervised versus unsupervised learning. So supervised is when you're given a set of right and wrong answers, and then you learn from that. And unsupervised is when you're just given a lot of text or whatever the data is, and you sort of learn the patterns that are explicit in them without being told what's right and wrong. I think it varies, again, from task to task. And we see a lot of cases where you can bootstrap off of a small amount of supervised data, where you need some of that, and then use that to label other data and so on. We're also looking at how you can move from one domain to another. So, you know, there's been some people have criticized the field of saying there's certain test sets are used too much. That you know, natural language processing is the study of optimizing parsing on the Wall Street Journal corpus. I don't think that criticism is completely valid, although you see some of that. And so people have started to look at how can you go from building a model there and then transferring it to other domains. And again, you know, we're pragmatic about that. If the best way to build a system is to pay people to label, then we'll do that. And we'll take that data. We'd like to have a system that doesn't require you to keep doing that, because you want to have something that's online, and as the world changes, you want to be able to change your model. But certainly bootstrapping from a smaller amount of supervised data is something we do all the time. Yeah?
So the higher, more data helps. Are you assuming that all the data are clean data? So could you make a general comment about dirty data, data cleansing, or are you making the assumption that the amount of good data is going to dominate the amount of dirty data? So
right.
maybe that the probability is going to take care of itself.
Right. So that's an excellent question, and I think you're absolutely right. So the question was about good, clean data versus dirty data, right? We saw that example where I said I suspect that many the instances of THEW were actually spelling errors and were not correct. So in that sense, the data was making things worse. And I think you do see that. So you know, the claim of this title here of this slide is more data still helps for this particular problem at this particular point in time. I don't want to say it always helps, because there is this trade-off. If the errors in the data were distributed independently, then more data would always help. But that's often not the case. Often, you know, the data that you find first is the good data, and then as you dig harder, you find lower quality data, and at some point you may reach this trade-off point where it's actually not helping. So you do have to try to clean it up, as I talked about using EM to clean up the spelling data. We do things like that. I often get this question of, well, you're training your translation system by downloading translations off the web. What happens if you start downloading your own translations or somebody else's machine translations? And I guess in the limit, that could be a real problem. We haven't hit that problem yet. But over time, we may want to worry about that. Yeah.
So children that learn 2 languages from the beginning get to see a lot less words. But by the age of 8 or so, would be able to translate certain expressions better than the current technology. Which means that there's still a room for more sophisticated modeling. And it seems, although I agree that we should use all this data, it seems that we will reach this point at which we actually need better models.
Yeah.
Now, when we reach that point, what will be the main difficulties? Will be ingenuity in designing those models, or just being able to deal with the computation?
I think it's both. So the question was, you hit these limits, and you're going to need better models at some point. And I think that's true. And I think for translation, we're getting near that point, where the model was a very simple one. It only goes so far. There's some languages where it does not do too well. So we're not doing that well in Japanese, Japanese to English, in part because the word order is so different. English is subject, object, verb in most cases, and Japanese is reversed. And yes, the model does have a move where it can swap things around, but it's difficult for the model to do that and get all the probabilities right. And so we've come to the point now where we also are applying syntactic models. Before, the only syntax we had was consecutive words. A phrase was a sequence of words, and there was no notion of noun phrase or verb phrase. Now we find that we need that to do better in Japanese. So we've hit a cutoff point where we can't do better without it. So that's part of it, is bringing in syntactic models, bringing in semantic models, and so on, learning to generalize, that you won't have to see a specific word in order to learn off it, but can you see a similar word and learn from that? We're doing all those things. In the beginning, you mentioned a child that knows multiple languages. That's an area that's very interesting to us. So I talked about translating from one language to another, and most of our models are built that way. But often you can't do that. So yes, I can translate from English to French because I have lots of examples of English-French translations. But say Latvian to Tagalog, I probably don't have too many of those. But I can go through an intermediate language. Often English is the intermediate language, sometimes Chinese, sometimes some other language. So I do 2 steps. And I have models for those 2 steps to a popular language than rather between the 2 rare languages. And that works better than expected. You'd think that you would double or square or something the errors. I think what usually happens is you make the same error twice in the same part of the sentence, so you only see it once. So that works well. We're also working in combining, rather than just going 2 steps to get from A to B, having multiple paths of saying, do this one, and then also do another path and another path through other intermediate languages and combine them all. That seems to help. We also do back off to other languages. So like we did Yiddish, not that much Yiddish text available. So we said, if you see a word or phrase that you haven't seen before in Yiddish, can you find the same or a similar phrase in Hebrew or Polish? And back off to those models that we know well. So I think there's a lot of opportunity for learning across languages. And intuitively, I find I do that. I go to Italy. I don't really speak Italian, but I know some Spanish and French and a tiny bit of Latin. And I can sort of paste things together by getting clues from multiple languages. And we want our systems to be able to do that too. In the back.
Do you think that this ability to gather data means that we should put statistics in some kind of early things to teach to people? Because for the moment, statistics is taught very often at the end of high school, and a lot of people don't understand statistics well.
No, I definitely think so. I think it's key to understanding the world, and I think it is underrepresented in our schools. And I complained about that. My daughter's middle school science fair You know, they all do their little experiments, and they have some statistical notions. So, like, they have the notion of being able to plot data on a graph of, you know, how much this frog jumped or whatever it was. And they have the notion of computing an average, but they don't have the notion of a variance. So, you know, they have no idea if the 6 trials that they did on their experiment is enough, or should they have done more. And I think those are notions that it's probably appropriate. An 8th grader could learn those notions, and they should be introduced then, and then they should be reintroduced multiple times along the way.
Now, these processes seem like they could be very largely automated. Where do you draw the line as far as what calculations you do ahead of time and store the results versus what you do on the fly when it's asked for?
Well, I guess that's an engineering question, and you do what's most appropriate. So we, like in translation, for example, we build this whole translation model ahead of time, and that's the most computationally intensive part. And then when we get a sentence, we compute the most probable parts of that sentence. That's easier, but even then, we do some caching of saying, we parse the sentence before. Let's have a cache where we keep around frequently asked for sentences, so we don't have to recompute them every time. And that's a trade-off we make in these kinds of probabilistic systems. It's a trade-off we make in all our systems of how do we minimize the computation? How do we minimize the network traffic flow by caching the right things in the right nodes in the network at the right time? And it doesn't necessarily have to do with the theory of statistics or probability. I think it has more to do with large-scale distributed system design of where you make those trade-offs.
I think we'll just take one more question.
All right. Yeah.
A lot of the learning comes from then the patterning with the data in place, but is there any sort of way in which the model self-corrects, especially like what you talked about with the common spelling mistake, where is there kind of like a recovery process and kind of learning in that from the common mistakes that it makes, and it kind of gets smarter down the line?
Yeah, so you can give it feedback, and that relates to the question we had before of the supervised learning. Of it makes a prediction, and then you can tell it whether it was right or not. You can tell that either explicitly by having somebody come in and say that was wrong, or implicitly by saying, I made this spelling correction suggestion. Did the user click on that suggestion? If they did, maybe that suggestion is right. If they didn't click on it, maybe it was wrong. Then you can feed that back into the model.
So I'm going to cut this off now. I want to thank Peter for a great talk. In the spirit of speaking of linguists, there was a linguist named Bar Hillel in the 1950s who said machine translation was clearly impossible because you have to have all of human knowledge in the computer. Right? So he gave the example of translating the pen in the box versus the boxes in the pen. The two meanings of pen there are quite different, and you wouldn't ever be able to understand that. And I think this approach might have some trouble with that example, but almost all other examples really works for it. And so I guess when you say that something is impossible, that's a red flag to a computer scientist, or especially to someone in AI. So I think Peter and his team have demonstrated that it is indeed possible. Thanks very much.